Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and this is the continuation of our lecture called Extreme Value Theorem. When last I left you, you were determining the critical points of this polynomial, and I hope you did it, but if you didn't, here's another chance. You know what to do. Let's see how you did. Well, we take the derivative, and when we take the derivative of this, we get this expression, and we're going to factor it. We take a common factor of 6x squared out, and we factor the rest of it, and we're setting this equal to 0. There is no place where this is undefined, so they're only critical points of the first kind here. So we set this equal to 0, and we conclude that there are three critical points: x equal -5, x equals 0, and x equal 3 over 5. Here's another function. Determine all the critical points for this function. You know what to do. Let's see how you did. You could use the product rule, but it might be simpler just to do algebra first. Sometimes it is. So what we're going to do is we're going to call this t to the 2/3 and distribute it through, getting this. We've only done algebra so far. We have not done any calculus. But now we're going to take the derivative of this term by term, getting this expression and this expression. And that is a -1/3 there. So now I can think about, I'm adding fractions, so I'm going to get a common denominator. The common denominator is going to be 3t to the 1/3. So I multiply top and bottom here by t to the 1/3, and over here I don't have to multiply top and bottom by anything, but it's all over my common denominator. Now if you look at this, there are two things going on. The denominator can be equal to 0 when t is equal to 0. That means the derivative is undefined there. So that is a critical point. And also the numerator can be equal to 0 when the denominator is not, and that is going to tell you that t is 1 over 5. So we have two critical numbers here, critical points. Here's another one. Determine all the critical points for this function, and this is a quotient rule. You know what to do. Let's see how you did. Okay, you might say, well, when I take the derivative, and I didn't do all the details here, and you should practice this and make sure you can simplify it to, into this expression, but what you can get is minus in front, w squared plus 14w minus 1 all over this denominator whole squared. Now this denominator is the same thing as what was in the function itself, so even though we do have places where that is equal to 0, those weren't in the domain of the function, and by the definition of a critical point, they have to be in the domain of the function. So we're not going to worry about those being critical points because they were not in the domain of the function. So that means the only thing we have to worry about is the numerator being equal to 0. And here you have to use the quadratic formula. You should check and make sure that you know how to do this. But you get two critical points, -7 plus 5 root 2 and -7 minus 5 root 2. Now here's a trig example. We're to determine all the critical points for this function, and we're going to do this with your calculator. So you know what to do. Let's see how you did. Now, so here was the function, and we take the derivative and we get this. Make sure that you see how this happens. The derivative of 6x is 6. The derivative of this, there's a minus, but the derivative of the cosine is a minus sign. And we have a 3 by the chain rule, so that's 4 times 3, and it's minus and minus is a plus. And so we get sine of 3x. Now we're going to be, that's defined everywhere, so we only have to worry about when that's equal to 0, and we get this. Now you really don't need a calculator for this one, because this is a angle that you know well. You could say, oh, 3x is equal to minus pi over 6, and you could have gone from there. But I want to show you and talk a little bit about the calculator, so we're going to use the calculator on this. So if we have a trig equation like this and we're solving it with our calculator, we'd find the inverse sine of that and we get this number. But now we have to think about what values that really is going to be, because you see the inverse sine of minus 1/2 or 0.5 is going to give you a angle that's in this quadrant, and if you want it to be a positive angle, what you'd have to do is go all the way around this way, or perhaps go from this angle up into that quadrant where it also has the same value. And so you're going to take this number here and you're going to subtract pi, and you get this number, which you see is what they get here. Or what you can do is you can do what I said the first time. Instead of going all around to 2 pi, you stop short of being 2 pi, which would be 6.28 something, and you would get this. So you see, that's how we end up with these as being values. And of course these could be plus 2 pi n, where n is an integer, either way. So you see, you get an infinite number of these. But now what we're going to do is, we really wanted to know about x, so we're going to divide both sides by 3, and we get that these are all of the critical points for this function. Here's another one. Determine all the critical points for this function. You see, you get to use the product rule and deal with the exponentials again. You know what to do. Let's see how you did. So we take the derivative using the product rule. So we have 10 times this second function, and we have 10t times the derivative of the second. Now that is going to be e to the u times du dt. Now when I look at this, I can factor out the exponential, which is appearing in both of them, and the 10, which is appearing in both of them, and I now have this as h prime of t is equal to this, having factored it out. Now the exponential is never equal to 0, so we're going to set this one equal to 0. We set it equal to 0, and we solve, and we get that our critical points for this function would be t is equal to plus or minus 1 over the square root of 2. Here's another one. Determine all critical points for this function, which is involving a logarithm and probably a product rule. You know what to do. Let's see how you did. Okay, so what we're going to do is we're going to take the derivative of this. So we're going to say the derivative of the first times the second, plus the first times the derivative of the second, and the derivative of a constant is equal to 0. We're going to simplify this and factor out the x. Now, and we're going to say, when is this equal to 0? Well, x can't be 0 because 0 is not in the domain of the natural logarithm. So what we're going to do is we're going to discard that root, but we're going to set this equal to 0. And then we're going to subtract 1 from both sides and divide by the 2. And then we're going to, this is the natural logarithm of 3x is this, so we can exponentiate both sides. And we conclude that 3x is equal to, and this is e to the negative 1/2. And so x is equal to 1/3 e to the negative 1/2, and that's 1 over 3 square root of e. And so that is the critical point for this function. Here's another one. You want to determine all critical points for the function y is equal to x e to the x squared. It's going to be a product rule, I think. You know what to do. Let's see how you did. So you do the product rule, so it's going to be 1 times e to the x squared plus the first x times e to the u. So this is going to be e to the u times du dx. And then we're going to factor the exponential out of this. Now, notice that when we do this, the exponential is never equal to 0, but this is never going to be equal to 0 either for a real valued function. So this function will not have any critical points. Okay, let's go full circle then. We've become expert at finding critical points, which is a first step in this process. So then we find all critical points. We evaluate f at all critical points and the endpoints of the interval. And you take the largest and smallest values, which you know exist because of the extreme value theorem. So here is a problem for you to do. Determine the absolute extrema for the following function on this interval. You know what to do. And we'll see how you did when we continue in 24.2.